Given a root of binary tree, imagine yourself standing on the right side of it. Return the value of nodes you can see from top to bottom. So, in this binary tree right side view, you have to consider like there is a person or yourself standing in front. So, what you can see, those that level you have to return it. So, you can see 1, you can see 3, and you can see 4, and that is what is the output is 1, 3, 4, right? But there are some cases wherein suppose this 5 has a 7 number also, then this person can see the 7, then we can include the answer as 1347. This we can include, this is I am telling, okay? But lead code can accept it, but you have to ask an interviewer whether you want to include this 7 or not. That will be a question for an interviewer. If because 7 is technically speaking, it is at the left side, it's not at the right side. Obviously for this road for sorry, for this route it is at the right side, but technically it is towards the left of this route. That's the reason you can ask this question. So to solve this question, this is pretty similar question to the one which we have solved, binary tree level order traversal. So here again we will have a right side list of integer. This will be a data structure which I will be using, and a queue data structure. Again, the queue I will be checking, like if queue is not empty, I'm just going to add according to the level. So all the levels will be, so all the levels will be added, like 1, 2, 3, 5 and 4. All the levels will be added from left to right. That's a compulsion which I'm trying to say here. And then we are defining here, before I enter into the in the queue, I'm defining as a previous tree node and a current tree node. So I am going to say that previous is equal to current, and you're polling the current. So you're going to poll the current, right? And when you're polling the current, you are adding that value in your previous. So all your previous will have all the right side because you're going to poll the current, and that previous you can put it into the right side of your list of integer. So for example, when you're adding 1 over here, then you will pull out this, right? But this is not pull out this, add this becomes your previous, add it to the right side. Then you're adding 2 and 3 over here, right? So previous and curve both are current, so 3 you will add into the previous, but you won't add the 2. You won't add the 2 because it is not previous. Previous and current are over here same. So whatever you're polling, you're polling the current which is previous, and that previous you are adding into the right side. Again you are adding 5 and 4 over here, 5 and 4. So 4 becomes your current because that is at the last. So current becomes previous, and that is again added to the right side. And so in the right side, you get 1, 3, 4. I hope you understood. So in the queue data structure, I'm adding 1. Before that, I'm initializing previous tree node equal to current tree node. Both are same. So one is my previous and one is my cur. Both are same, right? One is my previous and cur. So now one is pulled out and I'm adding into the right side. So one is added to the right side. Now once it is pulled out, I have to add the next level, the children's. So level is 2 and 3. So now my current is 3, right? My current is 3. So I will be polling 3. So current, previous and curve becomes same, right? The previous and curve becomes same. So I will be adding the current over here. That is 3. Once I add 3, then I go to the next level, that is 5 and 4. So when I go to 5 and 4, again my previous and curve becomes same, that is 4. I curve pull it and add 4 over here, right? And then whatever still queue is empty, that I can say that you return it as null. We don't need it. You just return that as null. We don't need it. That is a sentinel that I can show you how can I do in the code level. So whatever is pending, we just don't need it. You just return it as a null so that we just get an answer as right side. Let's code it and I'll show you. Like list of integer, uh, right side view, no true. First thing first, if root equal to null, then return new array list. This is like, you know that. Define on the right side array list, right side equal to new array list. Once we define this, what are we going to do it? We define it. Then we are defining, we are going to define the q tree node, q equal to new linked list. And here I'm offering q dot offer root because we have to add the root. Also, I'm going to offer null because it has to accept the nulls also so that we can use it in the latter part. Now, once this is done, while q is not empty, q is not empty, I'm defining a tree node cur and previous equal to root. Okay. So let me define this up itself so that we can use it. So cur equal to prev. Sorry, this is just an assignment, and I'm going to cur equal to cur dot poll. I'm going to pull it out. Okay. Tree node q. Create a method pool in the tree node that cur equal to q dot poll. So the first current value I will be pulling out. Tree node q is tree node, and cur is also the root, which is a tree node. So previous is initialize the variable. Okay, let me initialize the variable here. In prev equal to root. Oh, right. Once this is done, so here I'm saying while q is not empty, when the q is not empty, assign the root to the current, and that current is also same as the previous. This I'm telling it over here in this loop. Then I'm checking if, oh, sorry, while cur is not equal to null, what I have to check, that left childs are also not null. I have to check that. If cur is not equal, cur dot left is not equal to null, then q dot offer or dot left. So I'm putting all the left child and the right child into the queue. This is what I'm doing it over here. So this is another while loop because I'm just checking that it should not be null. And if it is null, then you don't have to check the criteria of right and left child. If it is null, then you just directly have to jump and use this. You just directly pull the pull. Basically, you just have to pull out that current tree node. You don't have to again use this. Dot left. You don't have to go and check whether left child is there or not, right child is there. You don't have to check. You just have to say previous equal to cur and you remove it. Once this is done, I'm going to say that right side you can add right side dot add dot value. This you can do it, and at the end what we have seen that there still that queue is not empty, right? So if queue is not empty, after doing all these things, still if queue is not empty, then what we have to do is just write it that queue is not empty, then we have to say uh, right side dot add null and return the right side, because we don't have to add anything, we just have to return null. And sorry, we just don't have to add anything. If even if the queue consists of, we just have to return add null into our right side and return our right side. This is what is the code, and it is O of n complexity. Let me explain you one more time. I have done, if the roots is null, then I'm returning a new array list. I'm getting a right side integer, then I'm offering the queue root and the null. This is just for our this is not, this line is not needed as such, but I am using this because it should not throw any exception. So I'm offering the root and as well as I'm offering the null. And when queue is not empty, I'm initializing this and previous as the same root, whatever is the current is. So this is what is written. And when queue is not empty, I'm just going to pull it and it is my current, and I'm going to add that in my right side. But if it has children, like here I have written, if it has children, then add the left and right side, and then you put it into your right side array list. Then you put it in your right side array list. And if queue is still not empty, then whatever is pending, you make it null, and I mean it's just null that you can add in the right side and return the right side. This is what is the code. It is O of n time complexity. Thank you.